Hello, my name is Dr. Elaine Blackwood. I'm Director of Sales and Marketing here at the company Photonics Solutions based in Edinburgh. So today I'm going to introduce you to a new generation of quantum cascade lasers manufactured by the company MirSense. So I'll just quickly go into sharing my screen with you and then we can begin. So operating CW at room temperature over the 10 to 17 micron wavelength range. In this presentation, I'll touch on some of the key parameters of operation of these QCLs, but then actually hopefully demonstrate to you how these QCLs are so well suited to high resolution infrared gas spectroscopy. So just firstly and briefly, just a little bit about Photonics Solutions. We're based on the Science Park here at Heriot-Watt University, where since 1999 we've been serving the photonics community in the UK and Ireland, where we've been working with some of the world's leading photonics manufacturers to bring their expertise and knowledge closer to the UK scientific research and also the industrial market sectors. It's always been our vision that we are really an extension of our manufacturing partner. We're here for first line technical consultation right from the very beginning, but then all the way through to installation and importantly after sales support for all the products that we supply. So as I mentioned before, MirSense are the manufacturer, and MirSense are our manufacturing partner for quantum cascade lasers. And it's out of their facility in Montpellier that they have mastered alternate QCL technology based on an antimonide. So unlike traditional QCL technologies based on indium phosphide, these new QCLs operate CW at room temperature in the long wavelength region from 10 to 17 micron. In MirSense's facility in Montpellier, they have total control of the whole chain of manufacturing, from design of the quantum cascade laser structures, the epitaxial growth of the material, processing of the devices in the clean room, all the way to packaging of the chips on submounts or into their HHL packages. Achieving CW operation at room temperature is quite unprecedented. Indeed, the majority of QCLs manufactured today do not operate CW at room temperatures below 900 centimeters to the -1. Achieving this CW room temperature operation is such a great achievement. That's one of the reasons MirSense have been recognised as, well, have achieved one of the top 3 positions. So they're a finalist in the PRISM Award 2021 in the smart sensing category. So on to basic molecules that we can detect using these lasers. So there are a host of molecules that can be detected in the 10 to 17 micron spectrum, but of particular importance are the BTEX pollutants. So this is benzene, toluene and xylene. It's well known that these are created as a byproduct in the oil and gas industry. For process control customers, measuring the highly poisonous hydrogen cyanide is important. If you look at the nuclear industry, it seeks to measure methyl iodide as they work to prevent nuclear plant accidents. Also, uranium hexafluoride is of key interest, again, as part of the nuclear industry, as part of the processing there. So now on to a little bit about these QCLs and the HHL package that these are integrated in. So to begin with, MirSense developed these distributed feedback QCLs with single mode emission and milliwatts of output power at room temperature. It's recognised for spectroscopy. The single mode operation is important. The wavelength is tunable with QCL chip temperature, but also with driving current, so take current as well. So temperature and driving current can all be utilised to tune the wavelength of the QCL. The very low threshold current, densities of approximately 10 milliwatts allow them to operate CW instead of just operation in purely pulsed mode. The standard DFB QCL is offered in the HHL package, which if I just zoom in here, this is the HHL package here, just this little, actually don't have the cursor up, but yeah, just the little unit here, little metal package is the HHL package. It has an integrated collimated lens with divergence basically less than 10 millirads, and it has a built-in tech element to control the chip temperature. So on the top left of this slide here, the chart shows the typical tuning of the laser that we use to measure benzene. So for a given temperature, so the lines here dictate given operating, so given tech temperatures. For a given temperature, when you change the current, you change the wavelength. When you change the temperature, you basically get continuous tuning. You get a continuous tuning range that you can sweep by changing the current. For the benzene laser, in this particular example, you can see when the chip is at 15 degrees, that's the red line on this chart here. So when it's at 15 degrees, you can continuously sweep over one wave number, and that's along the red line shown in this chart. This is achievable because of the narrow line width of these lasers. Typically over a long integration time of seconds, the line width is typically less than 200 megahertz. This is actually a very conservative estimate, and in fact, I'll show in the next slide that there has been work to demonstrate that this laser for use in high resolution spectroscopy, and we've managed to resolve species of line width down to 30 megahertz. So that's an order of magnitude smaller than this typical conservative estimate of 200 megahertz. The middle graph here shows an example of a DFB at 14.9 microns, which is again the absorption line of benzene. And this laser is operating at just 5 milliwatts, so it shows that we can target the absorption line of benzene with just 5 milliwatts of output power at room temperature. The top right graph shows the lasers have very low current threshold densities. You can also see in this bottom graph here that the beam shape, the beam profile as a function of distance is shown in this graph. So typically we see a full width at half maximum of the beam, which is 4 millimeters at the output of the package. But then if we move to about 1 meter from the package, you can see that the full width at half maximum increases to about 8 millimeters. I touched on this briefly, but these lasers have been used to measure sub-parts per billion levels of benzene. This is an outstanding result, and it was achieved by the Gazera company in collaboration with the University of Helsinki, based in Finland, and they were detecting benzene at 15 microns using a cantilever for photoacoustic spectroscopy. If I zoom in again, the benzene peak at 674 centimeters to the -1 was clearly detected. This technique worked extremely well, and the group was able to get a limit of detection below 1 part per billion. So for smart sensing, especially gas molecule sensing, which is really the relevant market segment for these lasers, what are the key benefits of these new antimonide DFBs, QCLs? What are the benefits for this particular market? So obviously, firstly, access to long wave spectrum is a great advantage for these molecules, like benzene, hydrogen cyanide, or uranium hexafluoride, all whose fingerprint region is beyond 10 micron. The central wavelength of these lasers can be precisely manufactured to hit right on the absorption band of the gas, adding to the flexibility. The lasers are also tunable over a few wave numbers, which again enables precise targeting of the absorption line of the molecule. As I showed in the previous slide, these lasers have very narrow line with typically less than 100 megahertz of free running. So for spectroscopy, it's extremely important to have narrow line width in order to precisely hit the absorption line of the molecule. The very narrow line width is what drives the very high sensitivity that can be achieved with these QCLs and enabling the low part per billion concentration. We've demonstrated the previous slide that we could measure sub-ppb detection of benzene. Output power is typically several milliwatts at room temperature, and it's been demonstrated that's often enough for absorption spectroscopy over long path lengths. The lasers are very stable over time, and that's important in spectroscopy, so you can decrease the detection over a long integration time. Low threshold current allows customers, clients to use these QCLs in portable battery operated systems because of the very low power consumption. So I just wanted to finish off by thanking Mearsense for their support with the presentation material, in particular Adrian Dakir and Dr. Roland Tessier. Roland is the chief laser scientist in charge of this new 10 to 17 micron QCL product line. So if you want to find out any more information about these antimonide QCLs, you can find out information on our website. Also, you can contact me directly by email if you wish. So hopefully the presentation has been of some interest. Hopefully it's demonstrated what we feel are some of the key benefits of this QCL laser and their relevance to high resolution gas spectroscopy. So I'd like to thank you for viewing online. Goodbye.